Hello and welcome everybody to Advent of Code 2023 Day 5. Um, so I don't know what's going on with this year, but this was a really hard one. I don't think I've ever remembered a puzzle this hard this early before. So yeah, it kind of caught me by surprise and really took a lot of time for me to solve this today. I'm not gonna lie. You can see it's getting a little dark outside. I'm recording this about 4:30 in the afternoon here in Ireland. Normally, I'm recording these at around midday, so it'll give you an idea about how much longer this took me to solve than previous puzzles. So yeah, a little bit difficult. It's not the hardest problem that has ever come up in Advent of Code, but definitely quite a challenge. And yeah, I struggled with it a bit today. So we're going to dive into it and talk through it. I'll talk about some of where I got confused. Could be you might have had a really good solution for this where you didn't get confused at all and it seemed super clear to you. But yeah, for me, this one, it hit me quite hard. So anyway, let's talk through the problem, talk through my solution, and then forget about this problem and forget that it ever happened. Okay, so day 5, if you give a seed a fertilizer. So the last we remember, we were borrowed a boat from an elf to go to find a gardener. Turns out this garden, it looks like it's more like a massive farm that is producing food for the whole island. So you go and you find an elf, and he tells you that the problem is that they can't turn on the water supply for the snow island because they need to filter the water first, and they don't have the sand for the filter. And for some reason, that hasn't been delivered. So you have to, he says there's a ferry that you can go and take. So we were on a boat, and we're going to get on a ferry to go over to check out what's going on with the sand delivery. But in the meantime, they have this food production problem, and he needs us to help with it. So we get given a copy of the latest Island almanac. And this basically has all of our information on it about how they're growing food. So it's a little bit convoluted. So bear with me as I explain it. But in any case, let's go. So the whole deal here is that we need to know how many seeds we need to plant in a specific location. Basically the idea is that if we're planting seeds have to be planted in certain locations. And where exactly those locations are is based on this map thing that they've given us, which is what they're calling the almanac here. So we have a list of our seeds at the very top, and those are just integer values. And we're told that there is then these different sets of maps underneath. So the first map is a seed to soil map, and then you got the next one is a soil to fertilizer map, and then you have a fertilizer to water map. So on and so forth, all the way down to a humidity to location map. So these are basically these like key value maps that are linking from a seed all the way down to a location. And the way in which they're linking is through soil, then fertilizer, then water, then light, then temperature, then humidity, finally to location. So that's what their data structure is. Exactly how it's modeled, though, is where it gets quite convoluted. So they say that these values are like mapped to each other based on ranges. So what that means is that if we have a seed value, say here in the first one of 50, we know that 50 will map to 98. So that's fine. So we go 50 to 98. So if we get seed value of 50, we know that corresponds to soil value of 98. But where it gets a little more complicated is that there's this third digit afterwards, and that third digit tells us for how many places after the first value this pattern repeats itself. So we've got 50, which goes to 98. So we have a 2, which means the next value, 51, maps to 99. And then after that, we're told later on that the values just continue as normal. So there's like a 1-to-1 mapping. But the thing is, we have multiple different maps as well. So we also have this one down here, this second one, which says that from 52 maps to 50, and that there are 48 of these. So we go 52, maps to 50, then 53 maps to 51, and so on and so forth for 48 more places all the way out to the end. So anything lower than the bounds of these ranges and anything higher than the bounds of those ranges, we're told just maps 1-to-1. So it maps just like normal integers would. And that pattern continues the whole way down for all of these. So there's multiples. You've got like, there's some here have 3, some have just 2. Yeah. And then, yeah, the values map across and they're varying different lengths and stuff like that. So already you can see this is kind of complicated to model mentally. And I'm not sure I did a good job of modeling it physically either, or in code. But anyway, we'll move on. So yeah, I basically described all of this stuff. Yeah, so effectively what they want you to do in this puzzle is take all of your initial values that you're given up here, and for each of these values, figure out what the soil location value should be. So follow the map all the way through and get to the end for each of them, and then report back what the lowest number that you got was. So yeah, that's what we have to do. Basically, have to traverse this big map and return the lowest value that we get out of looking at all these values. So, where this gets a little tricky, and if you just solved this on its own without looking at your input file, you would notice you wouldn't be very happy because when we go and look at our input file, I'm just gonna flash it up very quickly. Hopefully, no one will freeze frame it and copy it because you're not supposed to. But you'll see here now the values are enormous. So each value here is what is this? This is millions. So we're talking, yeah, like there's billions in values in here. So they're huge numbers. So if you were to try and make these like arrays that you just iterate through and map, you would very quickly run out of memory and you wouldn't be able to physically iterate through them. So what you have to do is you have to abstract your thinking now. So if you were considering of just implementing this problem by iterating through lists of numbers and seeing where things cross over, seeing where arrays cross over, that's not going to work. So with that in mind, let's have a look at the code I wrote for the first part and see what it's all about. So let's have a look. So here, this is our part 1 code. So the first thing to do is we need to parse our input and spit it all out. So I did this way it was kind of a way that occurred to me in my head to do this. So the first thing you need to do is you're going to need to get out the list of seeds. So you need to split that out. You can skip blank lines, and then if you find the line that is basically the starting what your next map is, I'm iterating an index of an array here, which is going to store this array up here. The almanac array is just going to store each of those maps one after the other in an array. And what it's going to store in that is from and to, which are 2 hashes, and they're 2 lists. So what they represent is effectively 50 and 52, or so I think it's the other way around. I think is it this way? Which way are they modeled? Which way is it? I think I made this mistake at some point. I confused myself, but it's... Where is it? I can't remember. Anyway, it's going to map a target to a destination. So there's a back and forth mapping there. And what I've done is, just store them in an array. So I know that the first index of this from matches to the first index of this to, and that's just how I've modeled the values. You could just, I think this was a silly way to do it. I should have just done this in like a 2-dimensional array, but it doesn't matter. This is the way I ended up doing it. And then the next thing you need to do is store each of the actual values. So again, this is my from and my to, splitting it out. But yeah, actually, sorry, the other thing I did here was I stored just the start and the end destinations of the ranges. So the from range that we start with, it's 50, and then say it goes to, I know it's of length 2, so then I just add on the 2 to it, so it stores 50 and 51 is the length of the range. hence the little -1 in here and the part adding on the third value. So we now have this array with all of our maps in it. So now we need to iterate through this and find, iterate through it, and we need to find where. Now this is, I can't even describe this. You'll see how much this broke my brain today. So we go through each stage of it. So effectively, we're going to walk this map effectively. So we start from the top, the first one, and then the first one will effectively transform all of our seed values into soil values, right? And then the next step, when we iterate through the next loop, it's going to transform those soil values into whatever the next one is. I think it's fertilizers or whatever. So as we loop through this list, we're effectively transforming those values each time as we go down, and then they'll form a new sort of lookup in the loop to check what the next values should be. So we start off with the first index of the map, and what I've done is I'm doing all the seeds at once. So for each, so it's effectively it's a two-dimensional loop. What I'm starting with is I'm only going to go through the whole map once, and at each step in the map, I'm going to do all the seeds at once, because I know there's only 4, so that's pretty easy to do. So I take the seeds, I need to figure out these sort of indexes. So if this is a range of values, I need to figure out where my seed falls on that range of values, and I also need to know in which of the mapped ranges it's in. So yeah, so because there's multiples, this is what I meant back here. So because there's multiples of these, I need to figure out, does it fall in this range or does it fall in this range? And then I need to know, well, okay, if it falls in that input range, then this output range is the one that I want. So that's the index, and then the value is based on where it is on that line. So we start off, we loop through that, then we start looping through all of each of the ranges that we have, and inside this we do this little comparison. So we can check if, so this basically tells us if we're in the range or not. So if we're not in the range, we can just skip. We don't need to do anything. If we are in the range, then we need to do something. So if we are in the range, we need to figure out what that offset value is. So this is basically the value from the start out, where that is. And then we also just need to log which index we're on, because then we'll use that to do the lookup later for what the 2 values should be. So if we do find a match, we're going to break out of this. We'll check if we match something. So if we didn't match anything, that means that the value of the seed didn't fall under any of the ranges that we checked. In which case, then the question tells us that we actually just transferred that value straight down. So that's like the 1-to-1 mapping case where it didn't match any of those transformation ranges, so we just put it into the next value as it is. So then at the very end, we update. So what I've done here is, so I remember I said earlier that we transform those values. So if we didn't match anything, we don't do anything to the value. So if it was the value 50, we don't do anything to it because it stays the same. So it stays as it is in the array, because that is also the valid soil value that it should be. And then if it is, though, if we did in fact find that it matches one of these transformations and we transform the value, we're going to want to update that to the new, what is the transformed soil value now instead. So for that, we use this map. So yeah, this is what this lookup is for the 2 value. We're using this from index that we found, and we're adding in the offset value that we found, which is how far along it was in that range, and that will give us a new value. So if we keep doing that over and over and over again, it'll give us at the very end all of the locations for all of the starting seeds that we had, and then we just need to return the smallest value of that, and that's our answer. So if I run this, it runs I think reasonably quickly. So on the sample, it runs, yes, 35 is the answer. And then for my input, it runs also reasonably quickly, not just a tiny bit slower. And that's the right answer for my input. So yeah, I'm sorry about the explanation for this because it's super hand wavy. I got there in churning through this code, and I got there, but it's not an intuitive problem for me. So I'm sorry, my talking through it isn't going to be the clearest. But let's move on to problem 2. This is going to be even worse with an explanation, I'm afraid, but I'll try my best to make it clear if I can. So what I really want to get to is actually just the bits of logic that killed me doing it. I'll just explain that, and then I'll hand wave over the rest of the code. It's a lot of it's the same, but anyway. So let's go down. Yeah, so part 2 now. Seemed innocuous enough at the start. But what they say is that the seeds at the start, they're not actually just individual seeds. They're actually pairs of values that define ranges, which is great. So what it says is that the first value is the start of the range, and then the second value in each pair is how long that range is. So for the example, what it tells you is it's a little bit sneaky actually in the example, the way it talks about it. It says, now rather than considering 4 seed numbers, you need to consider a total of 27 seed numbers. Which goes, oh, okay, yeah, that's not so bad. I can just run the same thing 27 times. And for the sample, that's absolutely fine. That'll work perfectly. That won't work for your input, because your input has, those massive numbers in it. So you're going to be going through millions, hundreds of millions of instances of this. You could brute force it. People did. I saw, I had a look on Reddit earlier on when I was in the depths of despair, and there were people talking about brute forcing it or flipping the problem in reverse and brute forcing it from the other end. And yeah, I didn't like that. And also, I attempted it at one point and realized that my code would take to the heat death of the universe to complete doing that. So I didn't do that. So yeah, we need to come up with some clever way of modeling things here, or clever way of approaching this problem so that we don't have to just try and brute force it. So I have some pictures here, which I'll show in a second. They might not be super clear, but we'll see. These are my sketches that helped me solve through it. So the way I thought about this problem from this point now was, so we're not looking at individual numbers anymore. Now we're trying to look at these ranges. So our input, our seeds, isn't just an individual seed. It's a start and an end seed range. So what you have to do is you have to try and figure out, does everything, or what happens to everything inside that seed range based on the mapping information that we have. And you don't have to do every single digit in between there. That's the real trick. All you have to know is you have to know the bounds of the bounds of your input seed range compared to the bounds of all of the maps that you have, all of the ranges you have in your map. That's what you need to do. And the real tricky part, so that when I say that now, that seems so simple, and that is, but the tricky part is just getting all the logic right to make sure that you've got all the windows sort of line up along each other. So I have some pictures like this, which I hope you can see. Maybe you won't be able to see them very well, but basically these are sort of the cases of the different ranges that you can have. So you imagine, say, this top case is kind of the most basic case you could imagine, which is where we've got, this is our map range, the outside one, and then inside it we have, our seed range is completely bound inside it. So these are the outer bounds and the seeds are completely inside it. But those windows can move around the place. So those windows can be like, you could have it so that it's like outside, then inside it, and then you've got 2 ranges that you need to look at. So effectively there's I think there's 6 cases. You could have to the left and to the right, completely outside it. You could have completely inside it. You could have overlapping from the left, overlapping from the right, or you could have completely overlapping the entire range. And yeah, you need to handle all those cases basically in your logic, which is where this code gets super messy. So the start here is basically the same thing, except I do some processing up here to give me those ranges instead of just individual seeds. And then the madness happens. So this big funky loop is where I handle all these cases. So these if statements, if I just compress these all basically just figure out the logic of where the window is. The very last piece, the piece that I said, there's only 4 statements here. There's 6 cases. 2 of the cases are identical, which is that it's either completely to the left of it or completely to the right of it, doesn't cross the window at all. And they're the same, basically. You don't have to do anything special for that. And in our logic, in the code, we know that the result is the same for both of those. We just copy them 1-to-1, which is what this little check down here does. Is so if it doesn't find any matches whatsoever, it just 1-to-1 copies them in. So we go through this big loop, the exact same kind of thing we did before, except this time we're checking ranges of values where they cross over. And the key difference is, instead of just checking a range value, seeing what it is, and then transforming it, or doing nothing and letting it copy as it is, we have to basically create some new ranges based on the one that we pass in. So this is where it broke my brain a little bit. So if you imagine, if you have, so I'm going to draw another picture, a fresh one, and throw it up here. So this is like an example of the way a range could cross over. So you see the long lines that I've drawn there, they represent the map values, and then the short are like, say, the seed range values. So you'll notice I've drawn 2 sort of, adjoining lines between them, which represents that if you were to try and split these up, you logically have 2 separate ranges in there now. You have a range of values that they do cross over for, and a range of values that they don't cross over for. If they do cross over, you need to pull that range out, you need to transform it, and you need to stick it into the list of ones to look at for the next time. So they're now transformed, converted soil values, and we're perfectly happy with that, and we store those. Then what you need to do is you need to look at the ones that didn't cross over, and you need to say, okay, I'll take those and I need to reuse those next time anyway, because we're told that there's 1-to-1 mappings. The only trick with this is, and this seems to work fine. I tried this and it just did not work. My logic, I was going down through all of my different ranges trying to figure out where the gap was, because it wasn't working. Where the gap is that if it doesn't transform, you need to keep that value and you need to run it again against all of the map values that you have. The reason being is that it might cross over with a different range that you have in the map, as opposed to just the one that you're looking at. That was the main difference for me. And in my code, that ended up being like a 1-line change, basically, or like a single word change in like 4 places. So these are, in my code, these ones here, these like really simple assignments here, are the ones where it's like it's the outside of the range. So what you need to do with these is, I do have this. So I have this thing of like these sub ranges. So I collect the sub ranges that match, and then at the end I transform them. So I get these sub ranges, and I'll log them into an array for the next time once I've got them all together. But instead of doing that with these guys, so previously I had these guys just mapped into the same subset, and then I'd pass them straight in as they were without rechecking them again. So what I do instead now is I just push them into the same list that we're checking, push them onto the end, so then the iteration will come back around and eventually hit them again. And there we go. And that seemed to solve my problem. And then the same thing at the end. We're trying to find the smallest limit, or smallest location. So once we get all of our ranges figured out down to the end, I'm flattening that because they're still in like pairs, but it doesn't matter, because if it's a pair, the smallest one has to be the smallest in the pairs. So you flatten it and then get the minimum value of it, and that gives you your answer. Again, I have to apologize. I'm not explaining this very well. I struggled a lot with today. So anyway, we are going to run this. So we can run day 2 for our sample, and that runs quickly, and that's the right answer from the sample. And then for our input, And there we go. Doesn't run too much slower than the main thing. This wasn't like a computationally very intensive problem. You kind of knew straight away that there had to be like a trick or a way of thinking about it that was going to do it, because brute forcing it is just not going to work. And this is it. So I'm very much done with talking about this one. I'm sorry if this isn't super clear, guys. This is probably the best I could do with this. So yeah, fingers crossed tomorrow's not so bad. It seems to be that the even days are okay so far and the odd days are tough. So if that pattern continues, then we just know to have a bit of dread for every odd day. But yeah, so anyway, that's it for today, guys. Thanks for watching, and I'll see you all tomorrow. Bye bye.